Okay, in this short video, we want to provide an introduction to the notion of basic simulation within Excel. Now, the basic simulation that we'll show will rely on the rand function for generating the randomness. Now, you've seen the rand function. It was part of the supply chain simulation sessions that we've conducted in the last couple of weeks with Dr. Gilbert. Now, so we're going to use just straight Excel to do the simulations here tonight. Now, there are some add-ins, like for example Risk Solver that came with the book, that allows you to do simulation, makes it just a lot easier in some cases to do various types of Monte Carlo simulation, for example. And then there's some customized or special software packages, specialized simulation packages called like Extend or Arena, or ProSim and things like that, which are, again, they're special programming packages or software packages that allow you to simulate very complex systems. For example, if you're simulating an entire manufacturing plant or a whole call center operation or something like that, those specialized software packages are appropriate for that. But in this course, what we want to do is give you a flavor for this notion of simulation, and we're going to do that through a few examples, and there's just some key Excel functionality that I want you to pick up along the way. Now, I'm going to assume, for example, that you're familiar with, for example, the Excel functions of VLOOKUP. I'm going to assume that you know something about data tables. We've covered that in the course. And also, I'm assuming that you know a little bit about just simply that RAND function, R-A-N-D, and then it's open parentheses, close parentheses. Now, if you need a refresher on those, in our Blackboard course here, there's a section called Excel Help over near the resources, and there are various articles and or videos that talk about those specific aspects of functionality. So what are we trying to do here in computer simulation? I mean, if you think about this course up to now, we did spent a lot of time working in optimization, and in many cases that was solving what we call deterministic problems. In other words, there were really no uncertainties. You were given the costs of the distribution centers and the transportation costs and the demands. They were all known, and then you were trying you were asking the model to prescribe a solution to you, which would be which distribution centers should be open or closed, and how you should flow the products from factories to DCs to customers, etc. So that was all what we call deterministic, because you already sort of knew what the final values were of all of the parameters. There was no uncertainty, if you will. So however, the world doesn't work like that. We saw when we covered the material and decision analysis that there's a lot of uncertainty. And so when we constructed decision trees, we were now comfortable in that world of uncertainty, saying, hey, we recognize we don't know exactly what the demand is going to be. It could be high, medium, or low. We don't know the probability of succeeding at a certain venture, for example. And so we were comfortable enough to put some values on that, some probabilities of these various states occurring. Well, simulation is sort of now an extension of that. It's sort of admitting to ourselves that we can't foresee the future, so we're not in the world of deterministic optimization anymore. We're recognizing that there's a lot of things that have uncertainty, and now we're going to build models to help us understand that uncertainty. In some cases, it's to choose a particular best solution, as we'll see, for example, in the heavy equipment or it's the heavy duty company example. What's the best system for replacing the machines? But we'll also see that in some cases we just want to sort of describe or get our arms around what the final results of something could be. And in doing so, we're going to characterize the variation associated with that. And that's what we'll show you how to do in the coin flipping example. But instead of a coin flipping game each time you play, that could be a pro forma if you're doing a financial analysis. And when you do that financial analysis and you realize, hey, there's some elements we don't know exactly for sure, how many units we're going to sell. Well, you can apply this type of simulation, it's called Monte Carlo simulation, to basically say, let's try a whole bunch of different values in there for the demand according to the probability that we see those events occurring, and then we can sort of characterize a distribution of what that potentially could look like. So for starters, again, as we move from deterministic to stochastic, again, a stochastic systems is one that evolves over time according to one or more probability distributions. In other words, it has some aspects of the problem that are in fact uncertain. Now, computer simulation, again, is a model, just like we build a little, model airplane to put in the wind tunnel to see when the wings fly off. A computer simulation is a model of of reality, but it just allows us to sort of test a model and see how it performs many times. So again, it's meant to imitate the operation of a system using those uncertain aspects to randomly generate the random aspects of the various events that occur in the system, and then observe how that plays out. So again, instead of operating a physical system, we're just doing it in an electronic way. Basically, we're simulating those events and taking a look at the performance of the system. Now, again, it's there's some cases where you can just do the math and figure out, for example, the expected value of something occurring, but simulation is best when it's too complex to be able to just sit there and scratch out the math to figure out what you expect to happen in this case. And so I'm going to show you I'm going to walk through the examples and add some additional functionality to what we see in some parts of it. And then in class we'll actually look at a few more simulations, ones that I've actually used in practice, developed for various applications. So the example in the book is this coin flipping game, and so you've won this opportunity to play this game at a casino, and so the rules of the game go like this. Each play of the game, so if you say, hey, I'm going to play the game, then each play of the game involves repeatedly flipping an unbiased coin until the difference between the heads and the tails tossed is 3. So you keep track of how many times you flipped, and you keep track of how many heads have occurred and how many tails have occurred. And when the difference in either direction is 3, then that's the end of the game. Now, the way the money works is you have to pay $1 for each time you flip the coin. And once you start a play of the game, you're not allowed to quit. And when you do reach that point where the difference between the number of heads and the number of tails is 3, then that's the end of the game, and they give you $8 at the end of the game. So, for example, again, here's 3 examples. If you said, okay, I'm going to play, and so you take out your dollar bills and you flip head, 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 well, guess what? You would have paid $1, $1, $1, but the game would be over now because you flipped 3 heads and now you've got 3 heads and 0 tails, so the difference between heads and tails is 3, and so they would pay you that $8. Well, that would mean you would have won $5 because you paid $3, $1 for each of the flips you made, but then you got $8 as a prize, so the net gain for you is $5. Second example, you flip a tail, then a head, then a tail, 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 which means you flipped 5 times, so you're going to have to pay $5, but you reached the end of it and you got your 8, so it's 5 minus the 8 is how you ended up walking away with 3. Now, if you're unlucky, you start flipping it, and you're keeping track. It's like 1 tail, 1 head, 1 tail, 2 heads, 2 tails, 2 heads. You're keeping track as you're doing each flip in terms of what's the total number of heads you flipped and what's the total number of tails. In this case, you had to flip 11 times until you got to the point where you had more tails than heads in this case. So in other words, you had basically 7 tails and 4 heads, and so you therefore reached the end of the game. The difference was 3, but the problem was you paid $11, $1 for each of those 11 flips, and then you got your 8, which means you actually lost $3. So you're not guaranteed to win in playing this game. You could potentially win, you could win as much as $5, or you could lose as much as, heck, I don't know, if it kept flipping back and forth between heads and tails, you could maybe lose a whole lot of money. So anyway, so we can set up a little computer simulation of this coin flipping game. Now, again, the computer can't flip coins. Instead, it'll generate a sequence of random numbers. And a random number is some number between 0 and 1 if it's been generated in such a way that every possible number within the interval has an equal chance of occurring. So that rand function in Excel, basically it's a random draw from a uniform distribution between 0 and 1. And we'll show you that here in just a second. So again, and that's what the rand function is. And so if you generate a random number in Excel, then you just simply assign one interval within that 0 to 1 value towards heads, and the rest of the interval towards tails. So in this case, if we do a random number draw between 0 and 1, and it comes out to between 0 and 0.5, we're going to call it a heads. If it came out 0.5 to 1, we're going to call it a tails. So that's how we're going to represent the random aspect of the flip of the coin and what you, as a result, get from it. So what I'm going to do here is I'm going to shell out over to, I'm going to discard that. I'm going to shell out over to Excel, and we're going to sort of dive into this coin flipping example. So I'm going to go to the basic sort of setup for the game. So here's what we're looking at here. We've got sort of inputs in terms of what's the required difference between heads and tails. As we said, the rules of the game say it stops when you get to a difference of 3. And what's the cash amount you get at the end of the game, which in this case is $8. So those are, again, shaded in light blue. It's the classic inputs that were given. Now, so what we've done here is we have simulated one play of the game. Now, one play of the game, and we've done this by potentially saying, gosh, if we were unlucky and we're going heads and tails and heads and tails, we're kind of covering ourselves to maybe as many as 50 flips might occur before we actually reach the stopping point of either 3 heads or 3 more heads than tails, or 3 more tails than heads. And so let's just look at how we're sort of simulating one play of the game. So we're going to generate a random number here. So here we are at, I'm going to zoom in just a little bit here. So we have, we're going to generate this random number, and if you look up here in the formula bar, it's simply, that cell is equal to rand times the open parentheses, close parentheses with nothing in there. And if I'm going to write here in a separate cell, I'm just going to say equals rand, and when I hit enter, boom, it gives me a random number, in this case 0.10369. Now, I can get it to redraw this random number that I'm representing in this function by going over here to formulas and over to the upper right where it says calculate now, and that will redraw the random number. Well, now the new number is 0.74612, and I hit it again. It's 0.75639. Hit it again, 0.68. So I can just sit here and hit calculate now, and I'm watching this cell F2 where I've put in this random number function. Now, there's a shortcut, by the way. If you say function F10, function F9. So if I do, actually it's not working on my computer right here, simply because I am doing this record. So it's limited in terms of what I can do. So nevertheless, you can do this calculate now, and it does a full redraw for any rand functions that are in your spreadsheet. Like if you look down here to the lower left, every time I hit calculate now, it's doing a full draw for each one of those random numbers. Okay, so let's get back to the play of the game here. So we flip the coin. In this case, it's the first flip. It came out with a random number of 0.31. Well, like we said, if it's below 0.5, we're going to call it a heads, and if it's above 0.5, we're going to call it a tails. And so you can look at these first two flips. The first one is less than 0.5, and we're declaring it to be a heads. And the second one is above 0.5, and we're declaring that to be a tails. And the way we do that very easily is we just, if we look at the function here, we've got if random number is less than 0.5, give it heads. If it's not, give it tails. So that's a very simple formula that is is throughout this. Okay. So we did this first flip, and we got a heads, and so now here we're just simply keeping track of we're keeping track of how many heads we have flipped thus far. So right now we've flipped one, we flipped the second time, and it came up tails, so now we've got one head and one tails. So all we're doing again is, as we go, we're incrementing either of these by one, depending on whether it was a heads or a tail. Now, over here in the right column, we're keeping track of the difference between the heads and the tails. And the way we're doing that is we're basically saying if the absolute value, which is the function ABS, if the absolute value between the total heads and the total tails is greater than that required difference, which was set at 3 for this model, then put in stop. In other words, say, whoa, this was it. We finally reached the point where now the difference between the two is 3, and we're done. Now, this is how we're putting this in. Now, once you'll notice here there's also the option that says if we haven't reached that difference, then just put in if we haven't reached the difference, then put in a blank. But if we have reached the difference and we have, there's no blank in the cell above it, then put in NA. So, for example, down here in cell G22, as I'm showing you here, so what we're doing here is the sort of the outer if statement says, hey, if G21 is blank, then or if it's equal to, if it's blank, then put in this or if it's, excuse me, if G21 is blank, then test it for whether it's the difference is greater than or less than or equal to 3. But if it's not blank, then put in this NA, which means not applicable, which means we wouldn't even really be playing this. We wouldn't be playing this game anymore. So that's sort of how that plays out. So basically the model is simulating flipping until the difference is 3. Then it gives you that signal for the stop, and then forevermore after that, it's of no consequence, the rest of these flips. Now, so if you watch, I'm going to hit, recalculate here, calculate now. So this one, it took 13 flips until we reached that difference of 3 between the heads and the tails. This time it did it in just 9 flips. Here it did it very quickly in only 5. This one, it took 19 flips until we finally reached that. So we would have definitely lost money on that. And as a matter of fact, that's what we have here in the yellow boxes, which are sort of our key outputs for a play of the game. This one, it took 19 flips. And so we paid $19 to do those flips, and then we won our $8 back, which means our net loss was $11 on that case. So that was a bad play. That would have been a bummer to have that. So anyway, so what we could do is once we set up this model, we could just sit here and look at these two yellow values, and if I'm most concerned with a cash, I'm really just going to look at this winnings value. It's like, whoa, that would have been bad. We would have lost $11. And then I'm just going to start hitting calculate now. You know, here we would have lost $7. That would have been a bummer too. Here we would have lost $9. Here we would have lost $3. Oh, but wait a minute. Here we start making $3. We lose $3. Here we make $5. Here we lose, or excuse me, we make $3. We lose $3. So we make $5. But you know, I don't know if if at the end of the day it's a good or bad bet. Quite frankly, I mean, it's jumping around. Sometimes we lose as much as $11 or even more, I guess you could. And other times I'm winning, $5. If I flip 3 heads in a row, boom, I'm able to get walk away with a net gain of $5. So once we have a model set up, now again, you could have a financial pro forma all set up, and you could have random values in there, using that rand function to represent demand. Like maybe demand is going to be somewhere between 0 and 1,000 units you're going to sell, and you don't know what it's going to be. So you could represent the demand in your financial pro forma, which is going to affect how many units you sell and therefore your revenue and so forth. So once we would have a model set up like this that has the random components within it, here's what we can do. So I'm going to go over to the next worksheet here, where basically I've got it set up now to basically have Excel automatically play this game a lot of times and keep track of the results. So what I'm going to do right here is basically equivalent to if I hit the recalculate 10 times and I wrote down exactly how many flips were going on each play of the game and what the winnings were as a result of a play. In other words, we're going to play the game 10 times now. And we do that using a data table. And again, I'm assuming you're familiar with that. So what I've done over here on the right is I've basically set it up as follows. I've just simply listed, well, I'm going to play it 10 times. So I say play, and then I've numbered it 1 through 10 to keep track of it. And here's the number of flips and the total winnings. Now, if you recall, when you set up a data table, you put in under this output you're interested in this case, it's equal to the number of flips, which is cell D6. Okay? And total winnings is equal to cell D8. I'm sorry, the first one was D7, and then the total winnings then is D8. They've got it name range of called winnings. So if you recall, you set it up like this, and then to do your data table, so you've got again these two basically outputs from the model you're interested in, and then you've got, in this case, just simply a count of how many plays you want to make. And so what you do is you select the table like this. You go to data, what if analysis, data table. Now, if you recall, when we've done data tables in the past, it's asking you to put the inputs. A classic data table is you're going to substitute in the values that are in the first column into some input in the model somewhere. Well, we really don't have an input that we need to put in. This is a very important point here. So all we're going to do in this thing called column input cell is I'm just going to pick some random cell that doesn't have anything important to do in the spreadsheet. So I'm going to put it like in cell K1 here. And basically that's where it's going to stick the values in the column that we have labeled as play. It's going to put 1 in there and basically hit recalculate. It's going to put 2 in there, it's going to hit recalculate. And then it's going to keep track of the results of the number of flips and the winnings for each of those. So as soon as I find my mouse here, I'm going to hit OK, and boom, it just did what we asked. So what it did is it played the game 10 times, and it kept track of the outputs reflected in D7 and D8, and it listed them right here. So check this out. This is the number of flips, and it looks like the sort of the worst case in our 10 flips that we had was we lost $5, and check it out, we won a bunch of times. As a matter of fact, I could say average, and I could compute the average of the number of flips, and I could just extend that over. But here's the funny thing, every time I made a change there, it actually redrew, random values for these 10 plays of the game. So now if I'm sitting here, now that I've set it up like this, I could technically hit calculate now, and it's going to be a redraw of, it's basically now 10 plays of the game. So now I'm getting a little better, more clear picture here. I'm like, wow, okay, look, I lost, there's one out of the 10 plays I lost $11. Let me hit it again. Oh my gosh, there was one play I lost $31. Another play I lost I could have lost, say, $15. So, and I'm keeping my eye on this average winnings, which doesn't look very good. It's like, for these 10 plays of the game, it's like seems to be losing, almost $9. Here we would have broken even. Here we would have lost $2.50. This isn't looking as good as a game as maybe, maybe we thought. Here we would have won on average 60 cents for each for the plays of the game. So that's cool and everything. Now, but I'm going to take it one more step further, and that is, yeah, a sample of 10 is pretty good, but I want to replicate the heck out of this thing. I want to see, like, on average, if I played it 1,000 times, what would be the resulting, on average, is it going to be a net gain on average or a net loss? Also, I want to characterize sort of what's the frequency distribution of how I could be winning or losing money on this. So I've got one more worksheet here, say with the large data table. So here's what I've done. It's the exact same thing I just did a second ago, but instead of just playing it at 10 times, I've actually now, I'm going to play it 1,000 times. So all I've done is, I've put in, and by the way, just to show you how to do that easily, the way you can do this is you just put in one, or here, let me kind of clear this out for a second, just in case you're wondering. So, like if I wanted to do 1, 2, 3, all the way down to 1,000, all I would do is put in 1, put in 2, then I would select the 2, and then when I drag the lower right corner, it just automatically, you can see it's automatically incrementing as I go down. So all I would do is crank this down all the way until I get down to 1,000 here, until my counter gets down here to 1,000, which is right about here. So that's just a kind of quick and dirty. Excel is smart, and it says, oh, it looks like you're sequencing something. So when you drag it, it automatically does that. So I'm going to set up a data table just like we did before. I'm going to select now those columns like that. I'm going to come back up, and I'm going to say data, what if analysis, data table. I'm going to, remember, I'm going to just, when I just want it to randomly redraw for the problem, I'm going to make sure I don't put this, I don't stick an input into anywhere important in the worksheet. So I'm going to stuff it into K1 here. And then when I hit OK, oops, hold on just a second. I'm going to put it into K1. And when I hit OK, then what happens is, again, it does exactly what we want, but now we're playing 1,000 different plays of this game. Now I'm going to check, I'm going to put my average, and this is going to be from N7 to N1006. So it's the average of that column. And I'm going to do the same thing over here. So that's kind of interesting. So again, I can even just now start playing with this. So I can go to formulas, start calculating. You know, our average loss was 87 cents per play. Here our average loss was 73 cents. Our average loss was 80 cents. So now that I've got this many replications of the game, I have now a lot more faith in the fact that, you know, I think the average sort of cash flow from playing this game is somewhere between 60 and 80 cents, basically. Maybe between 60 and 90 cents. So again, I can just, you know, here's $1.40 loss, here's $1.20 loss, etc. So okay, so it's somewhere between, like, looks like 80 cents and $1 probably on average. But it's definitely in the negative. So you wouldn't want to play this game if you had the chance to. Now, there's one more thing that I want to do with you, and this is very important, and this is especially if you're doing an analysis like in financial pro formas, for example. So we want to do a histogram, because here's what we've just observed. We've got now 1,000 plays of the game, and so I want to know, like, you know, what percent of those did we win $5? What percent of those did we, you know, lose $5 or $10 or $20 or whatever? So we want to be able to not only sort of report back to the decision maker what the resulting average loss is per play, we want to give them some sense for the distribution of the losses that can occur. So we're going to use something called a histogram. Now, you probably have seen this in descriptive statistics back in Stat 201 or 207, but here's how this works. So we go to Data Analysis, which is on our Data ribbon. We click Data Analysis, and one of the things in that list is a histogram. So we're going to select histogram. And when we select the histogram, it now says the following. It says, okay, so what's the input range? What's the input range that you want us to now sort of analyze? Well, I wanted to analyze all 1,000 values of the winnings. In other words, that's kind of the sample that we're interested in. We want to sort of get a sense for the frequency of it. The second thing you got to fill in here is, what is the bin range? Bins are simply, what's the size of the buckets that you want to do the counting on? You remember this from Stat 201. And so I've listed this here as, we'll do it as in this case, I put in these bins of -50, -45, -40, all the way up to +15. And then it says, okay, so where do you want the output of this sort of frequency histogram table to be? And I'm just going to say I want it to be right. I'll put it maybe right here at. Oops, sorry, that was the wrong one. This marks my bins, and I want it to output it. I'll put it right on the same sheet right here. And then I say, okay, and here's what it does. It goes through all 1,000 of those values that were in that column, and it keeps track of how many of them fell in the various ranges. And then it reports it right here as a frequency table, basically. So if we look at this table here, let me go a little bit larger here. If we look at this table, check it out. Now remember, we did 1,000 replications of it. So check it out. 500 or basically 56%, roughly 560 out of the 1,000, you won somewhere between $0 and $5. And 19% of the time you lost somewhere between -5 and 0. So as we look at this, like this frequency is how many fell in the range between -5 and 0. This frequency, 559, is how many fell between 0 and 5. This frequency is how many fell between 5 and 10. Well, none of them fell greater than 5. I mean, it's impossible to get more than $5 back in the play of this game. But check this out. There were 2 occasions out of the 1,000 that you would have lost somewhere between $45 and $40. You know, so the point is you have to be sort of aware of this. Now, here's a better way to look at this. I just select this data, and I say insert, and we'll just do recommended chart, and we'll say it smells it out, and it says, aha, it's like a frequency chart, and this is what it looks like now. So we'll put that over here. We'll scoot over here just a little bit. So again, now you can sort of see the way it's laid out. It's like, look, yeah, there's a 55, 56% of the time you're going to actually have a positive value, but the remaining, 44% of the time you're going to incur a loss, and in some cases you have to be prepared to lose as much as, $30, $40, dollars or so. So again, this is how you would characterize the result of that uncertainty in terms of how it plays into this problem. Now let me go back to our slides here, and I want to just push ahead because we've just covered all these, but I want to cover one more quick problem with you, and that is it's this heavy-duty machinery. Heavy-duty company, and here's the situation. So this is just a different style of a simulation. So this company has purchased a large machine for a new production process. The machine has this motor that occasionally breaks down and requires a major overhaul, which takes like 3 days to overhaul one of these motors. So what they do is they have a second motor, and the 2 motors are rotated in use. So one's in the machine working away while the other one is getting overhauled. And then when the one in the machine breaks, they swap it out and they then overhaul the one that broke. So that's how they keep this thing going. Now, the breakdowns always occur on the 4th, 5th, or 6th day that the motor is in use. And again, it takes 3 days to overhaul the motor, so a replacement is always ready. So, and here's some of the financials. To replace the motor, literally to swap out the bad motor and put in the good motor, cost $2,000, but when it breaks down in the middle of the production day, you lose some. It costs you money because you lose production, and you got to maybe work some guys on overtime or whatever. So you got a $5,000 charge when you interrupt production due to a breakdown, and then it costs $4,000 to overhaul the motor. After the broken one has been yanked out, you got to overhaul it. So basically, this cycle consists of, it costs you about $11,000 every time you incur one of these breakdowns and have to swap out the motor and overhaul it. So that's sort of the cost of a cycle, if you will. So here's the uncertain part of this problem, and that is you don't know exactly how many days it is until the motor, you put a motor in there, you don't know how long it is until it's going to break down and have to be swapped out. Now, again, there's 0 chance of it failing in the first 3 days, but there's a 25% chance of it failing after 4 days. There's a 50% chance of it failing after 5 days, and there's a 25% chance of it failing on 6 days. And then, if you add those probabilities, you notice that's 100%. So that's the entire space of what can possibly happen. So let's take a look now at this particular model. This is called heavy duty. And so this is the base model here. And here's the way they have this set down. So it's going to follow it basically through 30 cycles of breaking down and being replaced. So here's what happens. We start out, imagine at time 0, and we draw some random number. And now, using that random number, we're going to use VLOOKUP to reflect, did it break down in 4 days, 5 days, or 6 days? And so here's how we do that. We take the random number and we do a VLOOKUP on this table right here. And so if our random number for this first breakdown was 0.237, well, 0.237 falls below or less than this first value of 0.25. So it will then give us a so basically it's falling between 0 and 0.25. So it's going to reflect the number of days to be 4 days. So again, what we've done is we've taken this, what we call a discrete distribution, which says, okay, we got a 25% chance of 4 days, 50% chance of 5 days, 25% chance of 6 days, and we've reflected it with a little cumulative distribution here. So again, if the number shows up between 0 and 0.25, you're going to assign it 4 days. If it shows up as 0.25 to 0.75, you're going to assign it 5 days because it's that like middle interval of the 0 to 1 interval. And then if it's 0.75 to 1, we're going to assign it 6 days. So again, check it out here. This VLOOKUP is basically doing the following. It's taking the random number and it's looking it up on this little lookup table right here, J7 through K9. And the way VLOOKUP does is it looks until it hits one that is greater than it, and so in this case it starts at 0, and if it's increasing, if it hits to 25, then we would start looking at where it's going to stop going forward. But in this case, it's less than 0.25, so it's going to return the value 4. So again, I'm assuming you know how VLOOKUPs work when it's not an exact match. So we're going to rely on you to sort of review that if you don't already know that. And so check it out. The first random number here was 0.2372. That returns a 4 for the number of days since the last breakdown. 0.19 also is below 0.25, so it's returning a 4. 0.61 is between 0.25 and 0.75, so it returns a 5 days since the last breakdown. 0.83 is above the 0.75. It's between 0.75 and 1, so it returns a 6. And so all we're doing here is generating a random number, and then we're using this VLOOKUP call to this table here to reflect a random draw from that discrete distribution that has 3 separate intervals. That's how we're doing that right here. So what this does now is, this is basically identifying how long a machine is working until it breaks down and has to be replaced. Well, that got us through the first 4 days until then the one broke down. And when it broke down, it's going to cost us that whole $11,000, which is the cost to swap it out to the amount of lost production that occurs because it broke down while we were using it. And then it costs the additional $4,000 to overhaul it. So, and then the next one also, the one we replaced lasted 4 days, and then the one that we then it lasted, the one that we replaced lasted 5 days. So what we're doing is keeping track of the cumulative number of days that we're now able to sort of last by these cycles of replacement. And again, each time it's costing us $1,000. So this is sort of a nice little simulation, and what happens is you get down to the end here and you basically say, okay, the cumulative cost for 30 cycles was $330,000, but it lasted us 142 days. So if you take 330 divided by 142, you get an average cost per day for these breakdowns, overhauls, and swap outs and lost production the average cost then is $2,324. Now again, this is a random draw situation. So if I come over here and I go to formulas and hit calculate now, it'll do a redraw. 2171, 2245, 2171. So again, we're in that $2,200 range, which is kind of what you can expect. Okay, great. So now we can say, well, now wait a minute. Like, what if instead of waiting till it broke down, what if we and let me just go back over to here. So we said, hey, well, look, what if instead of waiting till it broke down, we would actually just schedule the motor to be removed and replaced at a certain time, like, every 4 days or 5 days or 6 days, even if a breakdown has not occurred. Now, the advantage to doing that is that if you replace it on your schedule, then you can replace it at night. You don't have to lose production during the day. So it changes the finances of it. So in other words, you do it at a convenient time, you don't lose any production. So the costs associated with this now are different. Instead of $11,000, they total $6,000. And that's because you're going to schedule the replacement of the motor on overtime. So it's instead of $2,000, it's $3,000, but you get to sort of overhaul it in a predictive fashion. So it only costs $3,000. So let's go back to our model here. And so now here's what we're going to do. We're going to basically replace we're going to replace it after 4 days. Now, on like a 4-day cycle. Now, what happens then is it either, like, the machine's going along and it's going to complete all 4 days, and then we're going to do that replacement at night. And if that's the case, then it only costs $6,000 for that cycle of replacement. If, however, it breaks down on the 4th day, which is the case that happens right here, then what happens is it broke down. We were scheduled to replace it that night, but it broke down that day. So darn it, we lost production. We incurred all of these costs associated with the earlier case. So what you see here is now in this model, again, depending on if it lasts 5 or 6 days, you notice that you get to have this planned replacement. So all of these are 5 or 6 days, and they got the planned replacement. Again, all these 5 or 6 days. But if it breaks down on that 4th day, you had that interruptive kind of breakdown, and it cost you more money. So hence the costs for the 5 or 6 day cycles are only at $6,000 because it wasn't interruptive. But the ones where it broke down on the 4th day, you're going to incur that higher cost. Excuse me. You're going to incur that higher cost of $11,000. So other than that, the model's basically the same in that we're just keeping track of the costs and the cumulative and so forth. And here's what we have now. So this now style of replacing it every 4 days, not waiting till it always breaks down, but if it hasn't broken down after 4 days, we go ahead and replace it on the evening of the 4th day. So it turns out that has a cumulative cost of about $205,000, and that was over 120 days. So if you divide those out, you get an average cost per day of $1,700. Now if we do calculate now and we keep our eye on that, now it goes up to 2,000, but now it's back down to 17, 16, 21. So we could do this a lot. We could even set up a data table to run this a whole bunch of times, and we'd find out that actually the average cost per day of doing this replace every 4 days, whether it breaks down or not, is actually cost advantageous to it. It turns out it's less than the $2,200 that we saw before. Now we've done a similar one for replacing it after 5 days. Again, the same thing, only now, check it out. If we're now replacing it only every 5 days, we're incurring a lot more breakdowns here. In other words, there's a 3 out of 4 chance it doesn't make it to 6 days if you think about it. And that's, in that 75% of the time, that's when we'd incur it breaking down during the production period and being a very costly interruptive kind of thing. So again, we can do calculate now for that, and it turns out that ends up with an average that's higher. So again, these are just 2 examples here, and these were, our original estimate was about $2,000 per day if we just always replace it after 3 days, but we want to explore replacing it after 4 days, 5 days, and so what we find again is that the 4 days is the cheapest option, and the 4 days is the cheapest option rather than the 5. So again, these are just 2 different styles. Again, sort of at the heart of this is that RAND function, that RAND function that allows you to represent the uncertainty within a model. We also looked at how we can use sort of the intervals of that random value between 0 and 1. We can use a VLOOKUP to represent discrete distributions when that's the case. We also looked at using data tables to basically like hit recalculate a whole bunch of times and keep track of what the output of the model was. So this is sort of the essence of spreadsheet, simulation, and at the heart of Monte Carlo simulation. So we're going to get a little more practice with this, with the practice problems, and also what we do in class. You'll find that this is just a super tool as you go forward, and you're starting to work on problems that again we know truly has uncertainty to it. Thanks for watching, and we'll see you in class. Take care.